Hi, my name is PJ Renda, and this is Controls Project 1 Arresters. So there were three main goals of this project. The first being that we were tasked with landing an F-18 fighter jet safely on an aircraft carrier using a given system for the cable that stops the aircraft. Second is using that same system, UAV must be landed, and then the results of that are going to be observed. And lastly, there's a new tunable water spinners that are being used to land the aircraft rather than the traditional dampers. Um, those water spinners will be used to land both the UAV and the fighter jet in this project. So I started off the project by looking at the model of the system and then immediately seeing that there are 4 springs, 2 dampers, 5 masses, and 2 pulleys. Um, the main thing is that they're all symmetric about a center axis that runs through and along the fighter jet, the exact center of the fighter jet. Um, the fighter jet itself weighs 20,000 kilograms and is landing at a speed of 64 meters per second. And the plane needs to stop before going off the edge of the aircraft, which is at 333 meters away from where it's landing. And then the pilot needs to survive as well, which is probably the most important part of this whole project, which means they can't experience a sustained G-force of 6 or more Gs. And I'm assuming that this is an experienced fighter jet pilot. That's what I meant to say, sorry. Anything more than 6 Gs will kill them, probably. So these are my free body diagrams for the 3 masses, as well as the equation of motions that go along with it. A couple of things here to note is that the values of K1 are the constant for K1 is doubled due to the fact that there's a pulley. It just accounts for that. And because of that, the value for K1 on mass 2, or the value for K1 pulling mass 2 is then halved to go back to its initial spring constant value. And that's just accounting for it in the equations, that 1/2. And the angle between M1 and the rest of the system can be ignored because as mass 1 travels farther away, it gets closer and closer to 0. And then also the mass 1 itself or the mass of the plane is halved in this case because of splitting the system in half. And that will stay as half the entire time. Alright, so here is my state variables again, the full state space model. The free body diagram's on the last slide, but I have the state space variables listed out. And from there, I got the free body diagrams, then the equations of motion, and I plug those equations of motion into the differential equation x dot equals ax plus bu, and that is shown in matrix form in that picture there. And then the C matrix comes from the equation y equals C plus D, I believe. And that C matrix is just outputting the distance mass 1 travels, or x1 as I define it. And then the B matrix is also, is zeros. There's no B matrix because there's no input force being applied to the jet. Alright, and then this is my Simulink model for the entire system. The entire project, actually, all 3 parts. It doesn't change. It's just a simple state space, and then a couple, my matrices are defined within that state space function, and then you take the first and second derivatives to find the velocity and acceleration graphs respectively, and that gain in there is just 1 over gravity, and it's just allowing me to get a graph of g-force versus time, which is a bit easier to read than acceleration. And then the out.simout is just exporting the data into Excel. So here are the actual results that I got when I ran part 1 of this project. So when I set the damper to a value of 300 kilograms per second, or the dampening constant to a value of 1,300 kilograms per second, I'm sorry, the max displacement of the fighter jet was 321 meters. You can see in the graph there it goes up to about 321 meters and then comes back down to around 240, maybe 235, and then evens out at around just below 250 meters. This is great because it doesn't oscillate off the aircraft, and as you can see in the G-force graph, the pilot does survive. The max sustained G-force is around 1.2 Gs, but there is an instantaneous G-force of about 6.2 Gs, and that is fine because it's completely instantaneous, so the pilot should survive. Alright, so part 2 of the project was landing the UAV with that exact same system. So nothing changed, the dampening constant is still the same, and with that, I guess what did change is the weight of the UAV is 550 kilograms, and the velocity is, or the mass of the UAV is 550 kilograms. I should say mass, not weight. And the velocity is 35 meters per second. Then also there is no pilot in the UAVs, so we don't care about the G-force that it sustains. And while doing this, the max displacement of the UAV is under 25 meters, so it stops really fast, but the cable actually is going to pull that UAV back beyond the initial place where it landed. So if it lands at the edge of the aircraft carrier and it looks like it's being pulled back around 12 meters beyond that, that could very well be in the ocean. I don't know if these pilots are landing right on the edge of the aircraft or not. I'm going to assume they are and that they can't travel back. So that is a problem. So this UAV with this system would be in the water if it landed. I guess it would land and then go back into the water. But yeah. Alright, so then the AAG system with the 2 tunable water spinners. So with this, nothing really changed in terms of the model. The damper, or the dampening constant, changed to account for these 2 water spinners, and these 2 water spinners can vary the distance they are apart, and that distance then correlates to how much the system will damp. And the range that I had found to be the range of distances that those 2 tuners need to, or these 2 spinners need to be within, is that range that I have listed there. That's a lot of zeros. I'm not going to say it, but within that range, both the fighter jet and the UAV can land if the 2 spinners can be tuned within that range. And then they both land successfully too, so the fighter jet pilot will not die. The G-force is not high enough, and the UAV will land without going back into the water. And then after that, I just have my MATLAB code in here for part 1, part 2, and then part 3. Yeah, I think that's all. Thank you.